Alright guys, I just wanted to provide one other example and actually go through the homework problem that we did on confidence intervals and basically help out with just seeing how this process works one more time. So let's say we have been asked to make an estimate for the proportion of students in the country who feel online learning is effective. Okay, so we're trying to get an estimate for students in the country, right? We're trying to get an estimate of the actual P, the proportion out of the entire population, right? We don't know what that is. Okay, so what we do is we go ahead and we get a sample. I get a random sample of 1,500. That's our sample size N. And we find that 615 feel learning is effective. So 615 could be like the X value. And to get our sample proportion, okay, remember the p hat is the symbol for that. All we're going to do is figure out what 615 out of 1,500 equals. And just by doing the division there, we see that that sample proportion is 0.41. Okay, so 41%. We generally do write these decimals out of 1 instead of writing 41%, where it's 0.41. Okay, so that's p hat. So what we want to do now to get our estimate, we're going to use a normal calculation in a minute here. So we need to first make sure that we have a normal distribution to work with. And the other condition is that we have a random sample so that we know that our sample will actually represent the whole population. So the random part was definitely given in the wording. Now for the normal condition, what you need to check, it's basically that the sample size and that the sample proportions are large enough to make the distribution approximately normal. We talked about binomial distributions earlier in the year. We kind of showed a bunch of examples, but basically what it boils down to for the normalness is that n times p hat needs to be greater than or equal to 10, okay, and n times 1 minus p hat also needs to be greater than or equal to 10. Okay, and remember we're using p hat here instead of p because we don't know what p is, but we do know what p hat is. Okay, when we did significance tests with the null hypothesis and the alternative hypothesis, we used p here because we were given a claimed value of p to use. Okay, but in these problems we're going to use p hat, so it's just a little simple calculation. The n value is 1,500 and the p hat was 0.41, and we just want to check that that's greater than or equal to 10. And what you should end up noticing, actually, when you multiply those two together, you actually get the 615. So we know that's greater than or equal to 10. And you can also show this one is greater than or equal to 10 as well. So show they're both true. Just give me your numbers just to kind of verify it. But basically, it's saying, are there more than 10 successes and more than 10 failures for the other one? And in both cases, those would be true. Okay, so if we wanted to come up with a confidence interval, again, our sample proportion is 0.41, so we're thinking that the 41% is kind of our estimate. It's called a point estimate. But since things vary, if you think about it, you have a normally shaped distribution. All these p hats here, we just showed it was normal in the previous step. Sorry, these are coming out a little sloppy. But we don't know where our p hat is, right? We could have had one of the p hats that was way up here or something, or we might have had this one. But the idea, when you create an interval, you actually take your p hat and you add and subtract some margin of error, and the amount of margin of error depends on the confidence level. And basically what it's going to turn out to be is taking our 0.41, and for 95%, if you go back to the other video, the number of standard deviations to capture 95% of data, if it's normal, we learned earlier the 68-95 rule, so 95% is within roughly 2 standard deviations. The critical value z star that we actually use is 1.96. Okay, and again, I showed where that came from using the inverse norm back in the previous video. So you have your 0.41 plus or minus 1.96 standard deviations. And remember, the standard deviation formula is just the square root of p hat times 1 minus p hat, okay, which in this example would end up being 0.59 over n. And it's the square root of that entire fraction. Okay, and just carefully do your work on that. I don't have a calculator in front of me right at the moment, but you should get 2 values, okay, because it is a plus or minus, right? You're going to do 2 separate problems. and you're going to get some value with the minus, some value with the plus, and you're going to write it out as saying we are 95% confident that the true population proportion lies between blank and blank. And the 0.41 should be right in the middle of your answer. So maybe the answers were 0.38 and 0.44 or something. I think that kind of sounds familiar, but make sure the 0.41 is right in the middle because that's where what you're adding and subtracting from. And then if you needed to be more confident, like part number 4 here, if we want to increase and be 99% confident, the only thing that's going to change is we are going to use more, a larger number of standard deviations. That z star value for 99% will always be 2.576. And then everything else is the same. You still have the number of the standard deviation here, just like it was before. Oops, sorry, I'm running out of room here. But then you'll just, again, do that calculation. And you'll just notice, again, you'll get two values. 0.41 will be right in the middle. Now, these values will be a little farther apart. You're getting a wider interval, right? With 99%, you're there. But with 95%, your interval might only go there or something. So if you need to be more confident, you just need to have a larger or wider interval. So, I mean, it's a little less precise or whatnot, but you're more confident it's in there because you've added more margin of error with the larger z star value. Okay, so hopefully that helps. Real quick example, and yeah, hope that does it for you. Thanks.